Welcome, future captains. If you're gearing up for your DGCA exams, you know navigation can be a bit of a challenge. So, today we're going to absolutely master Earth convergency and the conversion angle. And trust me, this isn't just about passing a test. It's about understanding the fundamental geometry of every single flight you will ever take. So, here's our flight plan for today. We'll start with the basic why behind convergency. Then we'll compare the two flight paths you need to know. After that, we'll jump into the formulas, uncover a really simple trick that connects them, and finally, we'll put it all into practice. All right, first things first. We have to establish a fundamental truth. We're flying over a sphere, not a flat piece of paper, and that one single fact changes absolutely everything about how we navigate. So, this is the question we need to answer. If you want to fly the shortest possible distance, why can't you just hold a steady compass heading? Why does the path look curved on a map? It all starts with how we define north on a globe.
Take a look at this. All our lines of longitude, the meridians, they're only parallel to each other right at the equator. As you start moving towards the poles, they begin to lean in or converge until they all meet up at a single point. This leaning in is the heart of what convergency is all about.
So here's the textbook definition, but let's make it simple. Convergency is just the angle between any two meridians at a latitude that you pick. That's it. It's a measurement of how much those lines have tilted towards each other.
And this slide just makes it crystal clear, doesn't it? Down at the equator, the lines are parallel, so there's zero convergence. But all the way up at the poles where they meet, you have maximum convergence. Everywhere in between, the angle just gets bigger and bigger as you go north or south.
Okay, so how does this create a real-world problem for us pilots? Well, this convergence forces us to choose between two totally different ways of flying from point A to point B.
This table breaks down the difference perfectly. A great circle, that's your shortest route. It's what your flight management computer is trying to fly. The only catch? Its track angle is always changing. On the other hand, you've got a Rhumb line. It has a constant bearing, which makes it way easier to fly by hand, but it's actually a longer, spiral path across the globe.
Now this is probably the most important idea to get your head around. As you fly a perfectly straight path, the Great Circle, your reference for true north, which is the local meridian, is literally rotating underneath you. So even though your aircraft's path is straight, the grid you're using to measure your direction is constantly changing.
So, the big question is, how do we calculate this change? Well, it's not magic, it's math. And this brings us to the first critical formula you're going to need for your exams. And here it is, the key formula. Convergency equals the change in longitude multiplied by the sine of the mean latitude. Now don't let the sine part worry you. Just think of it like a scaling factor. At the equator, it's 0. At the poles, it's 1. It just perfectly scales the convergence we see on the globe.
And a quick but really important note for your exams. Unless you're flying exactly due east or west, your latitude is going to change. That's why we don't just use the starting or ending latitude. We take the average or mean latitude to get the most accurate calculation. All right, let's keep building on this. How do we relate that ideal Great Circle track to the simple Rhumb line track? This is where something called the conversion angle comes into play.
The conversion angle, or CA as we call it, is the missing link. At any point on your flight, it's the exact angular difference between the super efficient Great Circle track and that simpler Rhumb line track. Now, here's the secret. This is the one insight that makes all the calculations just fall into place. That constant Rhumb line track is always perfectly in the middle of your changing Great Circle track.
This slide gives us the whole picture. The total change in the Great Circle's direction from point A to point B, well, that's the convergency. And as you can see, the Rhumb line track splits that difference perfectly down the middle.
So just remember this fraction, because that Rhumb line is exactly in the middle. The difference at each end, which is the conversion angle, is always 1/2 of the total convergency. Simple as that. Okay, time to put it all together. We're going to look at some practical steps and examples, just like the ones you'll see on your DGCA exams. We're officially moving from theory into the cockpit. I always recommend this 4-step process for any convergency problem. First, just sketch out the meridians converging toward the right pole. Second, plot your track across them. Third, draw a parallel line to help you find your angles. And finally, calculate and apply the convergency. Visualizing it this way is key to not making simple mistakes. Okay, let's look at two classic exam questions. On the left, we're flying from A to B. We calculate the convergency, it comes out to 8.5 degrees, and we add it to our initial track to get our final track at B. Now on the right, it looks a bit more complicated because we're crossing the 180-degree meridian, but you know what? The process is exactly the same. Use the formula, find the convergency, and then apply it to find that reciprocal track. You might be wondering, why does this matter in a modern glass cockpit? Well, it's because your automated systems, your INS or FMC, are constantly flying in great circle segments. At each waypoint, the aircraft makes a turn. That turn is equal to the convergency of the leg you just finished. It's happening on every single flight.
And finally, here it is, your exam cheat sheet. You've got the core formulas for convergency and conversion angle, you've got the key rules of track geometry, and you have the DIID rule, a really handy mnemonic. It stands for decrease, increase, increase, decrease, and it helps you quickly remember whether your track angle should go up or down depending on your hemisphere and direction. Memorize this slide and you are going to be well prepared.
So, I'll leave you with this thought. After today, you're no longer just connecting dots on a flat map. You are now navigating the true curved geometry of our planet. When you see that magenta line on your screen, you'll know exactly why it's curved. Good luck with your studies.